And hello, everyone. My name is Yuzhuo Li, and I'm currently doing a postdoc in elite grade research lab and in the Department of Electrical and Computer Engineering. Today's topic is about my research of graph theory inspired unified relationships in power converters. So let's begin. So first, I want to introduce some backgrounds of the power converter. It's actually to embrace the high penetration of the renewable energy. Both the current and future energy system will have a large portion of the energy be electrical form. And in practice, different electrical forms are needed for different application purpose. For example, we have AC or DC or high or low voltage ratings. So this is when the power converter technology comes in and plays a very important supporting role in our future energy system. So a power converter is basically a device that can convert the electricity into different forms. It can make the electrical power generation like more cleaner and better. And it can apply in different applications like the electricity light PV and wind turbine and electrical vehicle, and it can make the electrical power generation better regulated and can achieve the more efficient operation and lower the system cost. So most important, the power converter serves as a critical interface when we want to adopt the renewable energy into our grid. So here we take a look at the detail of the power converter. It can be a big and small one, and actually we use this such device everywhere in daily life. One example we may be very familiar is the power supply for our phone or for our computer. We use it to transform the high AC voltage into a low DC voltage for the computers or cell phones. A charge of the such device could consist of physical main parts and auxiliary parts. It may look quite simple and small, but actually in the inside, it's quite complex. The fun fact is that despite the complex look, the charger and the power supply can share some similarities in power electronics point of view. We see here a secondary side of the device and also a primary device. They separated by the transformer. Well, in practice, there's some more converters that could share the similarity, and we cannot easily tell. And in fact, a power converter is more than a simple box. So it normally involves quite a lot of technologies like power devices, microcontrollers, electrical magnetism devices, and so on. And assume that this is the first time you've seen or heard of the power electronic or power converters. How can you quickly get the general picture of this field? So this is quite difficult even for researchers like a PhD student. Power converter actually has a very long history and can be traced back into the late 19th century. And now we believe that the innovation of our field is going towards a mature stage. And if we take a look at the papers, we see that there's a burst of publications in just 2 recent decades, and the whole research community just flooded by the resemble power converter circuits and similar operation methods. And it's getting more and more difficult for people like some new students who just jump into the research field and to know what's going on and to want to make real contributions. And to achieve this goal, we need some powerful tools to help us learn the general picture of this field. And finding the relations in power converters is really helpful on this task. So how we can achieve this goal? And the answer is to find the right model through the proper mathematical tool. And my work is to apply a very powerful tool called graph theory for power converters. The graph theory has been popular in many electrical engineering areas. For different electrical circuits, we can build the graph models and find a unified solution for the uniform models. And following the same philosophy, we can apply to the graph-specific type of graph model for power converters. And we can establish the graph-based relationships among these different converters. So what are the advantages by doing so? You see, in traditional research methodology, we normally deal with one specific type of converters and find this problem and provide a solution for it. And if we encounter another converter, we're just going through the same process all over again. So we can imagine that there's a lot of different converters and a lot of different people studying that. It's like an island that each of us just isolated with each other. However, with the graphical relationship, we can have the boat among this island. So we can isolate it. We cannot isolate it anymore, and we can extend our knowledge of other types of converter, and we can use some existing solution for many other converters, like finding just one tiny problem and solution for a single converter, and we can transfer the knowledge to others. So this is when solving one is to solving all of them. So my work is specifically introduced two relationships called, one is graph duality, and it's very useful. And we can skip some details here. I'm afraid there's no time for the details. And another one is called graph isomorphism. And if you are interested, you can knowing that by doing this, by introduce these two relationships, we can achieve a lot of different works, finding new converters, finding new modulations, finding new topologies, new operation mode, and a new control strategy even so. And there's could be more. And thank you very much. And please ask questions as you want. Thank you.